Clarification has been something else suggested, as the speculation of the old vast effect varies. Evaluations made by a tremendous number of examiners support this thought, giving validation about how the universe began. In any event, the current universe of science, with new movements, brings us novel evaluations and points of view. These assessments challenge our perspectives, where certain pieces of information, for example, those from Neil deGrasse Tyson, have transformed into an immense contribution. This ever-evolving universe of science now brings something truly captivating. With the James Webb Space Telescope, we are witnessing discoveries that may make us question the speculation about the universe's beginning. The James Webb Space Telescope has discovered 750 new universes. These systems are not exactly as we anticipated, prompting us to rethink what we believed we knew about them. This discovery should help us appreciate how colossal systems developed. It is not surprising that this is stirring up how we perceive the unfolding of the universe. Previously, scientists posited that the Big Bang Theory was an outstanding explanation for how the universe began. According to this theory, about 13.8 billion years ago, the universe appeared through a perplexing event, akin to the incredible story of its birth. However, the photographs from the James Webb Space Telescope have challenged this idea. These images show galaxies that are subtler, smoother, and more mature, very different from what the theory predicts. According to the hypothesis, as the universe expands, objects should appear larger the farther away they are. However, these stunning images do not align with that expectation. The theory also states that, at the universe's origin, all matter was condensed into a singular, superdense point called a singularity. This phenomenon was incomprehensibly hotter than anything we could measure or recreate. This concept of a singularity originates from equations in theoretical physics proposed by Albert Einstein, called general relativity. Within the singularity, all the matter in the universe was compressed into a tiny, high-density space. It was a titanic amount of mass and energy squeezed into an incredibly small point. In simpler terms, experts have continuously asserted that the Big Bang Theory explains how the universe began. However, these new images from the James Webb Space Telescope are causing us to question that explanation. The galaxies it discovered do not fit the theory's predictions. Consequently, the theoretical explanation of the early universe may not be as robust as we once thought. From our current perspective, we see that all the energy in the universe originated from an exceedingly hot and dense point, the singularity. This point resembles the starting point for everything in the universe today. After this singularity, the universe began to expand and evolve over 13.7 billion years to become what it is now. The expansion began with an event many refer to as inflation, during which the universe grew at an unimaginable speed, far faster than the speed of light. Perhaps the very fabric of space itself expanded, stretching everything within it. This rapid inflation helped shape the universe by creating a uniform structure, paving the way for galaxies, stars, and other cosmic formations to form. As the universe continued to expand, the rate of expansion slowed compared to the rapid inflation. However, it still progressed steadily, a process influenced by dark energy. Scientists have observed evidence of this expansion through phenomena like the redshift of light from distant galaxies. Now, let's examine the breathtaking images of new galaxies captured by the James Webb Space Telescope. To most, these images appear stunning, showcasing diverse galaxies in a single frame. However, for scientists, these images pose a significant challenge. They do not align with their theoretical predictions. Firstly, these galaxies are unexpectedly mature, challenging our understanding of galaxy formation and evolution. According to the outdated Big Bang model, there should be significantly fewer galaxies, and they should not appear as developed as these images suggest. Additionally, the James Webb Space Telescope has revealed a far greater number of galaxies than previously predicted, further questioning the accuracy of theoretical estimates. Another surprising feature of these cosmic structures is their smoothness, which contradicts the expected irregularities based on the theory of how galaxies formed. According to the hypothesis, galaxies should exhibit anomalies and variations in their structure due to the chaotic conditions of their formation and evolution. Yet, the images from the James Webb Space Telescope depict galaxies that are remarkably smooth, lacking the typical complexity and roughness. During the universe's development, all its matter was initially compressed into a tiny space. As the universe expanded and cooled, changes occurred at the particle level. Protons, neutrons, and electrons began interacting with light and energy around them. These interactions played a critical role in the formation of matter in the universe. These early interactions between particles and energy laid the groundwork for the development of stars, galaxies, and other celestial structures. Over time, matter clumped together under the influence of gravity, leading to the formation of the large-scale structures we observe today. However, the smooth and mature galaxies captured by the James Webb Space Telescope suggest that this process may not have unfolded in the way traditional theories have proposed. One of the key predictions of the Big Bang Theory is that the earliest galaxies should appear irregular and chaotic, given the turbulence of the early universe. These galaxies should have displayed more variation in their shapes and structures. Instead, the James Webb Space Telescope has revealed systems that are surprisingly uniform and well-formed, even at great distances, which correspond to the early stages of the universe's development. This unexpected discovery has caused scientists to revisit their models of cosmic evolution. Could there be factors influencing the formation of galaxies that current theories do not account for? Could the assumptions underlying the Big Bang Theory itself need revision? These are the kinds of questions that researchers are now exploring. Additionally, the discovery of a greater number of galaxies than anticipated raises new questions about the distribution of matter in the early universe. According to the Big Bang model, the number of galaxies should align with the predictions made based on the initial density fluctuations present in the cosmic microwave background radiation. However, the James Webb Space Telescope's observations challenge this assumption, suggesting that the early universe may have been more complex than previously believed. The implications of these discoveries extend beyond our understanding of galaxy formation. They also challenge our broader understanding of the universe's origins and evolution. If the foundational assumptions of the Big Bang Theory need to be revised, it could lead to a paradigm shift in cosmology. New theories may emerge to explain how the universe came to be, incorporating the unexpected findings from the James Webb Space Telescope. As scientists continue to analyze the data from the telescope, they're also considering alternative explanations for the observations. Some researchers propose that the unexpected characteristics of these galaxies could be explained by changes in the physics of the early universe, changes that have not yet been accounted for in current models. Others suggest that entirely new physical phenomena could be at play, reshaping our understanding of cosmic history. One thing is certain. The discoveries made by the James Webb Space Telescope have opened up a new chapter in our exploration of the cosmos. They remind us that science is a continually evolving endeavor, one that thrives on questioning assumptions and revising theories in light of new evidence. The universe, it seems, still holds many secrets waiting to be uncovered. In the coming years, the James Webb Space Telescope will continue to provide invaluable insights into the nature of the cosmos. Its findings may not only deepen our understanding of the universe's past, but also help us anticipate its future. For now, these new observations serve as a powerful reminder of the vastness and complexity of the universe, and of our ever-growing capacity to explore it. In the underlying 2 or 3 minutes after the huge explosion, there was an interaction called nucleosynthesis, which included the arrangement of lightweight elements like hydrogen and helium. These elements set the stage for the development of stars, countless structures, and other complex components. As the relentless history unfolded, this blend of fundamental building blocks was a crucial stage in the universe's evolution, progressing from a primordial state of particles and energy to one where matter began to form as expected. The theory of the ancient Big Bang predicted scattered and chaotic galaxies. However, the JWST images tell a different story. Instead of chaotic, scattered galaxies, the photos reveal smooth, round, and spiral shapes resembling the structures we observe in the present-day universe. This surprising revelation challenges the belief that chaos is a common phase in galaxy development. If there are few or no violent events occurring in these galaxies, as suggested by the theory, it becomes illogical that small galaxies could grow to become massive. Similarly, the optical peculiarities predicted by the expanding universe hypothesis, where objects appear smaller with increasing distance due to expansion, do not seem evident in space. Experts have observed a striking pattern where massive structures tend to cluster in large groups, forming various connections across the universe. This large-scale structure aligns with the expectations of the theory of the universe's origin. According to the theory, the universe began in a very hot and dense state and then expanded and cooled over time. As the universe expanded, gravity played a significant role in shaping the distribution of matter and organizing systems. The gravitational effects predicted by the ancient Big Bang theory are consistent with what we observe today, with gravity shaping matter into cosmic systems and forming interconnected filamentary structures known as the cosmic web. The presence of these galaxy clusters and the cosmic web strongly supports the Big Bang theory. How galaxies are distributed across the universe aligns with the gravitational influences expected from an initially dense and expanding state. These elements, including the clustering of structures, the cosmic web, and the distribution of galaxy clusters, provide strong evidence that the universe evolved from a very dense state and has been expanding for billions of years. However, we must revisit the scale of the structures observed by the JWST. These images contradict what we thought we understood about the Big Bang theory. According to the theory, small galaxies should form and expand through interactions and mergers with other galaxies. Yet the galaxies captured by the JWST seem very different from this idea. If cosmic structures were interacting and merging as expected, we would see evidence of these collisions or mergers. Instead, the images show something else entirely. The Big Bang is still a remarkable theory. It is not merely a speculative idea, but is supported by substantial evidence, including observations of the redshift of light and data from distant galaxies. Studies showing galaxies moving farther apart support the predicted expansion of the universe. The distribution of light elements like hydrogen and helium throughout the universe is also consistent with the Big Bang theory. One of the most crucial pieces of evidence for the Big Bang theory is the discovery of the cosmic microwave background, CMB. The CMB is faint radiation that fills the entire universe and represents the leftover glow of the Big Bang. First detected in 1965, it still aligns with the predictions of the universe's origins. The observed properties of the CMB, its uniformity and temperature distribution, strongly support the idea that the universe was once in a very hot and dense state before undergoing expansion. This foundational aspect of the Big Bang theory provides an extraordinary glimpse into the early moments of the universe. It serves as a record of the initial stages after the Big Bang, helping to verify the scale of the universe's origin and evolution. The cosmic microwave background, CMB, not only supports the Big Bang theory, but also provides a wealth of data about the early universe. The slight fluctuations in the temperature of the CMB reveal patterns of matter distribution that eventually led to the formation of galaxies and larger structures. These observations match the predictions of inflationary models, which describe the rapid expansion of the universe in its earliest moments. The alignment of theoretical predictions with CMB data strengthens the credibility of the Big Bang as the most plausible explanation for the universe's origin. However, recent observations, such as those from the James Webb Space Telescope, JWST, have introduced challenges that prompt scientists to refine their understanding. The presence of mature and organized galaxies in the early universe contradicts traditional models that predict a more chaotic, fragmented state during those epochs. If galaxies formed and evolved faster than expected, it suggests there might be additional mechanisms or processes influencing galaxy formation that are not yet fully understood. This has led researchers to explore new questions. Are there unknown physical laws or phenomena affecting galaxy evolution? Could dark matter and dark energy, which make up a significant portion of the universe, play a more complex role in shaping structures than currently modeled? Is it possible that our interpretations of cosmic timelines need adjustment based on these new observations? Moreover, the detection of large-scale structures, such as filaments and galaxy superclusters, in the early universe adds another layer of complexity. These structures seem to have formed earlier than predicted, indicating that gravitational interactions might have been more efficient in certain conditions. Astrophysicists are also re-evaluating the role of black holes and star formation in the early universe. Supermassive black holes, often found at the centers of galaxies, are believed to regulate star formation and galaxy growth. Yet, their rapid formation remains a mystery. Similarly, the unexpected abundance of heavy elements in some early galaxies raises questions about how quickly nuclear fusion processes occurred after the Big Bang. The scientific community is now leveraging advanced computational simulations and upcoming observations to address these puzzles. Future missions, such as the European Space Agency's Euclid spacecraft and NASA's Nancy Grace Roman Space Telescope, aim to map the universe in greater detail. These missions will focus on understanding dark energy, dark matter, and the evolution of cosmic structures. Despite the challenges, the Big Bang Theory remains the cornerstone of modern cosmology. It provides a comprehensive framework for understanding the universe's beginnings, supported by multiple lines of evidence, including the CMB, galaxy redshifts, and the abundance of light elements. However, as new data emerges, the theory continues to evolve, demonstrating the dynamic nature of scientific inquiry. The journey to unravel the universe's mysteries is ongoing. Each discovery not only refines our understanding of cosmic history, but also deepens our appreciation for the vast and intricate cosmos we inhabit. Science thrives on questions, and the anomalies revealed by the JWST and other instruments are not roadblocks, but opportunities to push the boundaries of knowledge.